x parentheses n divided by 2. So in other words, that's half of the sample maximum. Do you have any questions about what we discussed last time? Okay. So part B here, we want to determine if the MLE is asymptotically unbiased for the expectation of x. And so how can we evaluate that? Say that again, please. Well, we can't say that theta is equal to theta hat. What we're looking for is to determine whether the expectation of mu hat is equal to mu. That's what we want to figure out. What do we need to know first in order to get that expectation of mu hat? Okay, so how do we get the expectation of it? Mm-hmm. But what do we need to know in order to evaluate that? We need to know the distribution of xn. Because are you familiar with calculating expectation as, I'll just use some arbitrary variable y. Expectation of y is the integral over all values of y times f of y dy. Are you familiar with this? Okay, so if we can find the expectation of xn, then we have the expectation of mu hat, because the expectation of mu hat is equal to the expectation of xn divided by 2. Because we can factor out the 1/2 from this. So for this, we need to know the density function. And the way I wrote it here, this is the density for y. Now, there is a formula to go directly to the density function for these order statistics, but we can work it out ourselves by looking at the CDF. So to find the density for say to find f sub x parentheses n, the density for x parentheses n, we first want to find large f x parentheses n, the CDF, or the cumulative distribution function of x parentheses n. Does it make sense why we need to know the cumulative distribution function? How do we go from the CDF to the density? No, it's the derivative of f xn with respect to x. Does that make sense? Are you familiar with that? Okay. So let me I should rearrange these. Okay, so let's talk about um, density functions and distribution functions. So we'll say here that for a continuous distribution, the density, the probability density function allows us to compute the probability that our variable falls within a certain region by integrating the density. So here, let's say that this is our density function, and we're looking at the probability of our variable being between two values a and b. This here, what I just shaded in green, is the probability that x is between a and b if this is our vertical axis here is f of x and our horizontal is just x. And because this is the area under a curve, we can find this as, or at least we can write it as the integral from a to b of f of x dx. importantly here, density functions always integrate to 1 across the whole region. So negative infinity, positive infinity, they integrate to 1. And mass functions, which I'll talk about in a second, always sum to 1. Mass function is the equivalent thing for a discrete variable. The mass function tells us the probability that the variable takes any particular value. So let's say I'm looking at values x here are 0, 1, 2, 3, 4, and my vertical axis is p of x. That's a common way to denote a mass function. Then my mass function might look something like this. And I said that all of these values have to add up to 1. And here the height of each is the probability that the variable takes that value. So height is the probability that x is equal to 2 exactly. Does this make sense? Okay. So then our cumulative density function, I should say abbreviations for these. So probability density function we write as PDF. Probability mass function we write as PMA. And cumulative distribution function we write as CDF. Or you'll also just see it as DF. I prefer CDF, so it doesn't get confused with degrees of freedom. But the for either a discrete or continuous distribution, and even for distributions that are neither fully continuous nor fully discrete, the cumulative distribution function gives us the probability that the variable is less than or equal to whatever value we put into it. And here for a discrete distribution, I'll do discrete because that's what we talked about most recently. We denote this as large F for either discrete or continuous, but for discrete, large F of x is equal to the probability that x is less than or equal to our input, little x. And this is the sum over all, I'll say, all xi less than or equal to x of the probability that x is equal to x, which is our mass function. And I should note explicitly here that p of x is the probability that, actually, no, I already have that for green. And so I'll copy this to use as a starting point for drawing the CDF. And instead of p of x on the vertical axis, this will be large F of x. And when we're looking down here first at everything that is less than 0, it's going to be 0 right here. And once we get to 0, it's going to jump up a bit. And the amount it jumps up is this height right here, which looks smaller on this one because I need more space for the vertical axis. But then it's continuing from there, the probability that x is less than or equal to 0 stays the same between 1 and 0 until we get to 1, and now it jumps up again. And the height it jumps up is the height of that second bar there. Stays flat until 2. And then here's our biggest jump up to 3. And these things should be shorter so that I have enough space. The jump up to 3 is about twice as high as the jump up to 2 was. I mean, sorry, the jump up to 2 is what we're at now. So here's our jump up to 2. And then our jump up for 3 is a little bit shorter. And then our jump up to 4 is the shortest one. So this is our CDF corresponding to the PDF we saw on the first one. And importantly, the smallest value on our y-axis is 0. The largest value is 1. Because we get to a point where, or at least for just the discrete distribution, we get to 1 up top. For this particular distribution, we get to 0 on the bottom. For any CDF, the limit as we're going to infinity is going to be 1. The limit as we're going to negative infinity is going to be 0. If we look at, for this particular distribution, anything that's greater than 4, the probability that x is less than or equal to 4 is 1, because our only possibilities are 0, 1, 2. Does that make sense? Okay. The difference between what and what? Well, the important thing here is that we're looking at a less than or equal to. So it's not the probability that x is equal to any particular value. It's the probability that it falls on the region going all the way from negative infinity to whatever we're plugging into the function. That's the difference there. Does that make sense? And this should here, sorry, this should be xi. So we're adding up all of these mass function values that are less than or equal to what we're putting into our CDU. What do you mean by that? It's the integral from negative infinity to x of our density function. Well, one's an integral, one's a sum. So are you talking about comparing the continuous and the discrete? Because we can, um, I mean, it's an entirely different operation. It's a sum instead of an integral. Um, like, I mean, if you go into like the deep theory of this, they are the same, but for the purposes of your class, they are like an integral and a sum are two totally separate things. Um, mhm. So this one we're adding up distinct steps. Um, for the continuous case, and I just have this here so that I know what to draw. I just need to be able to look at this. We're starting here at 0. I guess a tiny bit above 0 because I didn't go quite all the way down. But then and I should get rid of these zeros. We're going up a bit steeply and then leveling out somewhat. And then it can be, okay, we're going up increasingly steeply up until that peak there. And then we level out a bit. No, we don't go down. F of x is always increasing. But we level out and then go a bit steeper. And then we level out entirely. And this thing, that's about it. This thing again is still starting at that 0 value and going up to 1. But regardless, we can say that for either the continuous or the discrete case, every CDF is always non-decreasing. We see with this discrete case that it's flat for most of the time and then jumps up, but it never decreases. It's always either staying level or going. And for any CDF, like I mentioned before, the limit of the CDF as x approaches negative infinity is 0. The limit as x approaches at positive infinity is 1. And for the continuous case specifically, not for the discrete, but only for the continuous, the density function here, f of x, is equal to the derivative with respect to x of large f of x, the CDF. And so that's how those two are related. The discrete case, we can't differentiate that. It's just not a differentiable function. But these are very important things to know about these distributions or these functions. Mm-hmm. Yes. Yes, both of these are continuous. Here I'm saying that the CDF is the integral of the density. Here I'm saying that the density is the derivative of the CDF. Okay. And then, have we talked about expectation at any point? Like how to actually calculate it? Okay. So here for expectation, in the continuous case, actually for either continuous or discrete distributions, expectation can be thought of. Sorry? No? That's on your end. Do you need to answer a call? So expectation for a continuous distribution, expectation of x is the integral over the entire domain of x, negative infinity to positive infinity, of, or whatever your domain is, of x of f of x, sorry, f times f of x dx. Now this is different than what we have above, because for one thing, we're integrating over the entire real line, not just up to the value x, but also we're multiplying here times x within that integral. For a discrete distribution, the expectation, very similarly, just that we're taking the sum instead of the integral. We're taking the sum over all values of x times the mass function evaluated at x. Or in other words, x times the probability that our random variable big X is equal to little. Does that make sense? Okay. And we might as well talk about variance while we're at it, because this is a very important thing to know as well. Variance is the expectation of x minus mu x squared, which we can also write as the expectation of x squared minus mu x squared. And here mu x is a shorthand for the expectation of x, which is in line with our thinking of expectation as being the mean of a distribution. And we can evaluate this expectation of x squared by using the property that for any continuous, at least, function g, the expectation of g of x for the continuous case is the integral of g of x f of x dx. For the discrete case, this is the sum over all values of x of g evaluated at little x times the mass function evaluated at little x. And so that allows us to then write this expectation here, the expectation of x squared, or the expectation of x squared minus mu squared, or sorry, the expectation of x minus mu squared, in terms of either the integral here or the summation of g of x times p of x. Does that make sense? Okay. So going back to our problem here, we need to know the density function to find the expectation, and we need to know the CDF to find the density function. So let's find the CDF. We can write that f for x parentheses m of x is equal to the probability that x parentheses n is less than or equal to x. This is just our definition of the cumulative distribution function. Now, remember that x is the maximum, x parentheses n is the maximum of all of the variables in our sample. So if x parentheses n is less than or equal to x, what can we say about the other variables or the other values in our sample? They're less than or equal to x. So we can say here that since x parentheses n is the largest value in our sample, if x parentheses n is less than or equal to x, then every value from x1 up to xn has to be less than or equal to x. So that's how we'll write it in the next step here. This is the probability that x1 is less than or equal to x, x2 is less than or equal to x, all the way up to xn is less than or equal to x. And remember here that this xn is the sample maximum, but this xn is just the nth value in our sample, in whatever the order the data. And this is reminiscent of how we got x parentheses n in the first place, is that we said that if the product here is equal to 1, that means that every xi has to be less than or equal to theta, and that means that x parentheses n has to be less than or equal to theta. So this is sort of like going in reverse for this one. And so we get this. And now how do we break this up? Okay. In order to break up the joint CDF here, which is what we're looking at, we're going to apply one of the same properties about our sample that we use when breaking up the joint PDF. So it's something that we can say about x1 up through xn that is very important to being able to split this out. It is that all of our variables are IID. Allows us to, which means independent and identically distributed. So since they are independent, we can break this up as x1 less than or equal to x times x2 less than or equal to x, and so on, times the probability that xn is less than or equal to little x. And we know that they are identically distributed, so all of these things here are the same function. So this is just the probability that x, which is just any generic value from this distribution, sorry, any generic variable from this distribution is less than or equal to x raised to the nth power. And so again, we can split up the joint CDF because of independence. And we will reduce this to a single CDF because x1, xn are identically distributed. And this is a CDF. We don't need to write it as a CDF because we're going to write it in terms of the density function in the next step anyways. But this, just as a note, is equal to large F of regular x, parentheses x. Does that make sense? Okay, so this is the probability that x is less than or equal to x. We can find this using the density function for x. So how do I write this in terms of the density of x? We're not working with 1 to n anymore because we've simplified this into just looking at what we call the common distribution for these variables, which for us is the uniform from 0 to theta. So up here we have our density, which was, that's the general case. Here's the density for this particular distribution, was 1 over theta on the interval 0 to theta. And so if we have the density, we're looking for the CDF. The CDF is the integral of the density over the entire range, or not the entire range, sorry, over technically negative infinity to little x of f of, and we can use any old placeholder variable, t, dt. But this here, the negative infinity, we can just replace with 0 because in our distribution, we are only, our smallest possible value for x is 0. So we'll just start integrating at 0 because the density is 0 anywhere x is smaller than 0, or in this case, we're plugging in t to the distribution. And so this is just going to be 1 over theta dt to the n. And technically this is wherever x is between 0 and theta, because that's where our density is. Above theta, it's going to be 1. But then what is this integral here? What is the integral of 1 over theta dt? We don't know theta. What we found before was the maximum likelihood estimator for theta. We are never going to like have a value for theta, because theta is unknown. We were estimating it before, but the integral is not with respect to theta, it's with respect to t. So we just need to evaluate this integral. What is the antiderivative of 1 over theta with respect to t? Yes. Well, we're increasing the degree of t. Right now, t is to the degree of 0. So we're going to end up with this is our integral here is going to be equal to t over theta evaluated from t equals 0 to x. And so this is just going to be x over theta. And so then this comes out to x over theta to the n. And this is our CDF for xn, x parentheses n. What we want is the density function so that we can evaluate this at, so that we can compute the expectation. So we're looking for the density for x parentheses n. How do we get that from the CDF? Okay, so we're going to differentiate the CDF. Remember that to go from a CDF to a density, we differentiate. When we went from here a density to a CDF, we integrated. And so here we're going to take the derivative with respect to x of f sub x parentheses n of x. Just d dx. I'll write this as theta, x to the n over theta to the n. And what is that derivative? It's going to be n times x to the n minus, and I'll write it as like this, n times x to the n minus 1 over theta to the n is our density for x parentheses. And of course, this is still for x between 0 and theta. Okay, so now we have what we need in order to find the expectation of x parentheses n. And how do we write that expectation in terms of this density that we? How do we write the expectation in terms of the density? So expectation in general, we can write as the integral over the whole range of our variable of x times the density of x dx. So that's what we'll do here. And the range of x, like we said, is 0 to theta. It says x times f of x dx. And so this is n over theta to the n, x to the n, dx. The integral is going to come out to n over n plus 1 times theta x to the theta. Does this make sense? Oh, sorry, I'm not x to the theta. Theta to the n, sorry. N plus 1. And then we can combine like terms here. And, oh, sorry, no. This should be theta to the, there we go. That is, and so then we have n over n plus 1 times theta. This is correct. And we said before that the expectation of mu hat is equal to the expectation of xn divided by 2. So this is going to be n over n plus 1, and I'll write it as 1/2 n over n plus 1 times theta. Does this make sense? Okay. So then what was the question? Is it asymptotically unbiased for the expectation of x? What would you say about this? So what we're looking at for asymptotic unbiasedness is whether the limit as n approaches infinity of the expectation of oh, I'm sorry, this should have been mu. The expectation of mu hat is equal to mu. That's what we want to know. And so that's the limit as n approaches infinity of this thing right here. And how do we evaluate that? I can factor out everything that does not involve n, and this will be theta over 2 times the limit as n approaches infinity of n over n plus 1. What is this limit? The limit as n approaches infinity of n over n plus 1. So um, they have the same degree. Leading coefficient is 1 for both. And so this is going to be equal to 1. And so our limit of the expectation of mu hat is theta over 2. And this is equal to mu. So our estimator for, or I'll say the maximum likelihood estimator for mu, which is just defined as the expectation of x, is asymptotically unbiased. Okay, I need to go now, but I'll put the Zoom recording as well as the whiteboard. Actually, once I update this PDF, it should upload automatically. That'll be in the Google Doc, and then I will see you tomorrow at 8 p.m. Kuwait time. Thank you, Seth. Have a good one.